Okay, the kid and the sled. So on this problem, we've got a kid pulling a sled with his dog on it across the snow. We know some information, including the coefficient of friction and A. On the basically, we want to do a free body diagram here. So let me see what I got. Notice the free body diagram only indicates the forces. I'm not including the components or anything like that. I have the weight down. I'm calling W. You could have just as easily called it F sub G. I would have avoided calling it mg simply because there's more than one mass, unless somewhere else you had defined maybe m equals 24 kilograms, something of that nature. Or you could have written mg as long as you remembered to include the two masses later on. So for this one, I just went with W. I stuck with N for the normal force. You've got the friction force in there, and you've got tension at that angle. Over here on the side, I showed that I know Ty is T sine theta, and Tx is T cos theta, because we've got this triangle in here, right? Your X and your Y, X and Y, etc. This part was only worth 2 points. There's several things I'd be looking for. You had to include all the correct forces, you couldn't have any extra forces in there, etc., etc. B, we want to know the normal force on the system. Take a look at the work. Here I'm setting up Newton's second law, I'm doing my dynamics. I'm looking at the y dimension, and I know it's in equilibrium. It's not accelerating up, not accelerating down. I'm identifying the positive y forces first. I have my normal force. I have my y component of tension. I'm subtracting the downward force of weight. Looking for the normal force, so I isolated n. Paid attention to recognize that my weight was actually both masses times gravity. And then I subtracted T sine 20 to get 216 newtons. Sorry, part B ended up being worth 3 points. I was looking for proper setup for your dynamics formula, proper substitution, isolation, and answer with proper units. C wants to know the acceleration of the system. Doesn't imply anywhere that we're in constant velocity. In fact, turns out that the boy and the dog and sled are all accelerating. So, what we have to recognize here is that by setting up Newton's second law, the net force in the x dimension is accelerating. So we have ma, which is equal to that right word, x component of tension minus the friction force. Isolating A and then plugging in the proper setup for Tx, and then also recognizing that Ff is mu Fn, which in my case is mu n. Went ahead and plugged in the numbers. Should be able to follow it completely. And you get an acceleration. Okay. Part C ended up being also worth 3 points. Now at this point, this is basic dynamics. This is the stuff every single one of you needs to be able to do without too much struggle. This is worth, the first 8 points of this problem, all of you should be able to nail. You have to make sure you can get to this spot. Make sure anything on this page that's not, sticking in your brain, you come in for help, and we'll have to try to figure this out together. Now, I do believe that the rest of this problem is doable. However, we start to go away from the fundamentals, we start to kind of kick it up a notch. D wants to know the distance they travel. Assuming for rest, they travel for an additional 6 seconds. This ends up being one-dimensional motion kinematics. Or going back to that first week of school stuff, make your knowns list for this part of the problem. It says they are starting from rest. So the initial velocity is 0. We know the average acceleration is that 0.85 meters per second squared. We know they're going to travel for that 6 seconds, and we're looking for that change in D. You get to this equation. VI is gone. VIT is gone because VI is 0. Plugging in your numbers, you find that travel a distance of 15.3 meters. Now at this point, this one was worth 3 points as well. It is not dynamics at this point, so I can see where you get to a kind of a during the headlights type of thing where you can't remember what to do next because you are in a path doing your force work, and then the wrench is thrown in. But if you really look at it, this here is also some of the more basic kinematics type of problem. Again, I genuinely believe you all should be able to get to this point. And if you haven't yet, not a problem. It will be a problem, though, if you move along without trying to make sure you're here, because we're going forward. But this is going to be important information the rest of the year. Okay, and E. Sorry, wrong thing. E here. We have, at the end of that 6 seconds, the boy lets go of the sled. We want to know how much time passes before that sled dog system comes to rest. So this one ended up being quite a big part of the problem. Definitely the most time-consuming part of the entire test took place here, because we have a lot of stuff that we have to really take into consideration. First of all, the dynamics is changing. We don't have that forward and upward force of tension. That turns everything around. It basically means that the only source causing it to accelerate is the frictional force, and it's actually causing it to decelerate. So let's first figure out our new acceleration. Our new acceleration comes from sigma f equals ma, which is going to be negative ff, or ff, but ff is to the left, so I'm calling it negative. Rearranging for a, we get to the point where we know a is going to be equal to mu fn. And so why don't we just use the fn from an earlier part, right? Well, we can't, because if we look back at my previous dynamics, we see here that earlier fn was equal to the weight minus that upward tension. However, the upward tension's gone. That normal force actually goes up. The ground has to do a little bit more effort to keep that sled and dog in equilibrium. So over here, I show my work for that. I'm showing that I know that n has to equal mg. And thus, I'm plugging it in, and I'm going to get a totally different acceleration here. I have a will end up being mu g, which ends up going to 2.1 meters per second squared, and it is negative because it's to the left. Now we can use that with my one-dimensional kinematics. I know my acceleration is negative 2.1 meters per second squared. I know my final velocity needs to be 0. I don't know how long it'll take to get there, so I'm looking for. And then what is that initial velocity? Now, there's another kind of change we have to recognize. That this initial velocity is indeed the velocity all the way back earlier on, which I don't even remember what part it was. Alright, we have to actually solve for that velocity. So we have the knowledge that way in the beginning, they started from rest. Let me use my d values. Oops. Let's look at part D here. Part D, we know the initial velocity is 0. We know the acceleration is 0.85. We know for the first 6 seconds it's accelerating like that. I want to figure out the velocity at the end of that first 6 seconds, and that'll be my initial velocity in this part down here. So we have to do that first. So basically, that top info here, I'm showing that my initial velocity at the top is 0, times this, or plus this product right here, 0.5 times 6, shows at the end of the first 6 seconds, I'm traveling 5.1 meters per second. Now that is actually going to be used in the final tail end of part E here. Because remember, I'm looking for time. I now know I have a change in velocity of that value, because I've got to go to rest. So my change in velocity is going to be my final 0 minus the 5.1 over that 2.1 acceleration I had way over here, showing that it takes approximately 2.43 seconds for the dog and the sled to come to rest. Now, I believe the dog would have jumped off by that point, so perhaps everything would be different. But assuming the dog stays on the sled, 2.43 seconds to come to rest. This ended up being a 4-part pointer, rightfully so. There was a decent amount of work that you had to do to get to this right answer. So, you know, that's actually a good thing, because if you didn't get to the right answer, but you did some elements in here, you were able to get pressure credit. If it was if it was a lower point value, it would be difficult to award pressure credit for this one. So, okay, that is the end of this problem. I don't think up until part E there was really anything that was outside of a normal kind of type of problem for dynamics and kinematics. E, you rightfully kicked it up a notch. So I'm hoping that after looking through this, you'd comfortably be able to get at least 11 of the 15 points, and possibly even a few more, and hopefully for some of you, all 15 points here.